Fine.
Okay. So good morning to everybody. Today is a real pleasure and an honor for me to introduce you Alvio Renzini. I think that all around the world, Alvio is really well known, but just for the young people that are connected today, I would like just to remember some achievement obtained by Alvio in his career. He got his degree in physics at the Scuola Normale Superiore in Pisa, and after several fellowship in different places. He has been full professor at the theoretical astrophysics at the University of Bologna, and then he became also director of the astronomy department and of the astronomical observatory in Bologna. For 10 years, he has been VLT program scientist at the European Southern Observatory. He is a member of the Accademia Nazionale dei Lincei, and he also we can call him commendatore because he obtained this appointment by the president of the Italian Republic. Okay, so for sure we can say that his work is one of the main pillars in the context of stellar and galactic astrophysics. And just to give you an idea of the level and the relevance of the scientific activity made by Alvio, I would like just to remember that he has been author of about 500 papers on peer-reviewed journal with about 70,000 citation and an issue index of about 134. So I think that this number give a clear idea of what is the level of the research performed by Alvio. Today, Alvio will talk about a scenario for the formation of a galactic globular cluster in the context of the multiple stellar population phenomenon. So please, Alvio.
Yeah, thank you, Santi, for your nice introduction, and to you and to Michele for the kind invitation to give you this talk. Before I start with the presentation, I would like to say just 2 words about Italo, who left us at the beginning of this week. He, together with Franca, they have been extremely productive on their own individual scientific trajectory, so for saying. They have really done a very original work and opened up a specific research issues in stellar evolution. So I wanted to mention this because he was really a nice person. So let me try to start my presentation. Hopefully it will work. Sharing.
Yes, that's perfect. Now you show your presentation in slide view. You open.
Yes.
We can see your screen.
Okay.
Yes, that's
okay.
Good.
So this is the outlook.
Perfect.
Let me start with this consideration. This issue of the formation of globular clusters is really intriguing. It's unresolved, and yet nature has been able to do them all over the place at all times. So it is really a very challenging problem because we are facing a phenomenon that has been extremely common, and yet we don't understand so far how the globular clusters formed along with their multiple stellar generations. So I will try to tell you what is my tentative solution to this problem, which is still partial. So let me go through the outlook of the presentation. I first will mention the properties of multiple stellar generations, which is something really very basic, common virtually to all globular clusters, especially those in the Milky Way, for which we have direct proof of it. And the question is, where globular clusters formed in the first place, in which kind of environment. The next issue is what stars have made the material for the second generations of stars within the globular cluster we see today, and also eventually what was the globular cluster formation process. I was not sure I will have time to touch about the next issue, which is what about the metal-rich globular clusters, because they present another challenge to some extent. And supposing, and finally, I will spend a few words expanding on this issue. That is, if the scenario of globular cluster formation I'm going to present you is the right one, assuming that it is the right one, may not be, what will be the consequences for other aspects of astrophysics? What I'm going to say is essentially based on an article with Anna Marino and Antonino Milone that appeared last year on Monthly Notices. So the multiple stellar generations, let me go through briefly. We have some classical examples from photometry, the globular cluster 2808 from the Space Telescope observations back in 2007 by Piotr et al., in which you see multiple main sequences, and which, by the way, can only be interpreted with different values of helium. And then on the right side, you have the spectroscopic evidence for multiple populations in the same cluster from Carretta et al. 2009, in which you see that oxygen and sodium are anti-correlated, and oxygen drops by more than an order of magnitude in some of the stars, as oxygen essentially is converted into nitrogen, whereas a part, even a small part of neon makes proton capture and becomes sodium, since neon is originally far more abundant than sodium. There is not much need of, there is not many neon nuclei that are eventually converted. Now, still in the same cluster, Milone et al. Invented this that we now call chromosome maps, that are combinations of different filters on the Space Telescope, in particular the UV filters. And you can see that in this particular case, several different spots in this diagram on the upper right corner corresponds to bunches of stars with each with a specific combination of CNO nuclei and helium. Another example of multiple population is another in this cluster. In the middle panels, you have the chromosome map. You see that there is a sequence which is nearly horizontal that we consider to be those we call the first generation stars, as their composition is more likely stars in the general field and not being part of clusters. And the second generation instead are this elongated sequence at nearly 45 degrees on this picture. And on the right panel, you see what is the effect of changing various compositions, the composition of various elements on the chromosome map. And the main trend for the second generation is one which is basically a combination of nitrogen increase and helium increase. So you have a combination of those two arrows that you see over there. Now there are chromosome maps, thanks to Milone et al. 2017, for 57 globular clusters, and you can appreciate they are all kind of similar, but with peculiarities. Each of them is slightly different from another. And so the question is basically, what are these chromosome maps telling us about the formation process? And what we have here is on the top panel the fraction of stars, sorry, of first generation stars as a function of the luminosity of the clusters or their total stellar mass. And you see that the so-called first generation is in almost all the clusters a minority. In the most massive clusters, the 2G, the second generation, makes up to 80% of the clusters. And even in less massive clusters, let's say those around 10 to the fifth solar masses, about 50% is still second generation. And the second generations are all helium enriched, thought by various degrees. The majority are increased, the helium increase is relatively small, of order of 0.01, 0.02, but in a few cases it can go up to 0.1 in mass fraction. So in the substantial increase in helium. And so those objects are kind of rare. The last evidence about multiple populations that I want to show you is this one from a recent paper by Dondolio that use near infrared filters on space telescope, and you see that below the so-called knee of the main sequence, the knee corresponding to the beginning of formation of H2 molecules in the atmosphere and in the envelope of these stars, the main sequence bifurcates, and we can distinguish again 1G and 2G stars by the fact that in the F160W band there is a strong water vapor, and therefore 2G stars that are oxygen depleted are brighter in F160, or vice versa. 1G stars that are oxygen rich and therefore water rich are blanketed in this band F160W. So that's important to realize that the multiple stellar generations go all the way virtually to the bottom of the main sequence. So in summary, the observational constraints on the origin of globular cluster multiple populations are summarized in this view graph. Multiple populations are essentially specific to globular clusters. In the general field, stars with abundance patterns seen in multiple populations are very rare, while they are dominant in globular clusters. Variety, which means there are very different situations from one cluster to another, so having in general a common kind of scenario. Discreteness is another very important issue in the sense that in most cases there does not appear to be just a spread in chemical abundances, but the chemical abundances come in bunches. So for say, there are groups of stars that are chemically homogeneous with different composition with other group of stars inside the same cluster. Supernova avoidance is also an important issue in that in most cases, but there are exceptions, the second generation stars have the same metallicity, mean iron abundance, as the first one. But there are a few exceptions, which are also important, by the way. A critical issue that has over which we have agonized over the last 20 years or so, is that in order to produce this dominant 2G population with specific composition, one needs the first generation donors of the material to make second generations need to be of order at least 10 times the mass of the globular cluster today, or 10 times the mass of the second generation. But the question is always, where are they now? Then once the question comes of the nature of the first generation donors, one has to have objects having temperatures hot enough to produce proton capture material, such as sodium, for example, and also having an helium enrichment, as I mentioned, up to about 0.1. So understanding how all this came about is still, as I mentioned, an unsettled puzzle. And there are very much, people are very opinionated, and so the situation is so far very polarized. Above all, the concept that I want to mention, stress to you, is the following: that the evidence, if we just look at the chromosome map, the evidence is that the globular clusters kept forming stars as in a runaway process, difficult to stop once it started, and the star formation efficiency, that is conversion of gas into star, had to be extremely high, order of close to 100%. This means that the formation of first generation stars did not stop shut further star formation, that actually went on and on and on in a series of bursts in some cases, in other cases in a more continuous way. If what is the typical star formation efficiency in today's molecular clouds in the galaxy, this is universally seen as order of 10%. If it was 10% also in the formation of globular clusters, that would increase by another factor of 10 the mass budget required to make the second generation. And this would bring the so-called budget problem up to another factor of 100, which really would bring us, it would make the puzzle even stronger. So the evidence, I would say, is that the ongoing first stellar generation formation did not inhibit the formation of star formation further to produce the second generation. And second, that the efficiency of star formation had to be very high. Now, the next question is, where did the globular clusters form in the first place? Well, the case of metal-poor globular clusters that formed most likely in dwarf galaxies at high redshift. This is an idea that goes back to Renzini 1978. Sometimes it is referred only to the classical case of Omega Centauri, which was seen as the nucleus of a dwarf galaxy now dissolved. But in reality, the concept was first proposed for all globular clusters, not just the most massive ones. In the best case we have of a globular clustering formation within a dwarf at high redshift is shown in this picture. That is due to Eros Manzella of a couple of years ago, in which what you see is a lensed galaxy by a foreground cluster of galaxies. And this little galaxy has a mass of about 2×10⁷ solar masses. It lies at redshift 6. And you see the nucleus, what is called the core, is an object of 10 to the 6 solar masses with an effective radius that is less than 13 parsecs, and which in fact appears as perfectly point-like in this image. So we have only an upper limit to the radius. So 10 to the 6th solar masses within order of 10 parsec. What else could it be if not a young globular cluster? Here we have another example from still from Vanzella, from another lensed dwarf galaxy at redshift 4, in which the galaxy itself is this linear stream as a string, as it is lengthed by the foreground galaxy cluster. And you see that there is a number of spots in it. Each of them is a young stellar cluster, and their masses range from 0.7 to 4 10 to the 6 solar masses. So this looks really like an assembly line of globular clusters in a dwarf galaxy at redshift 4. Let me now go to the third issue in this presentation, which is what kind of stars made the material to make the second generation. Now, here, everybody has presented their own pet candidate, in the sense those working on massive stars were immediately proposing massive stars because they were more familiar with them. Those making fast rotating massive stars, of course, expanded on it and proposed this kind of objects as the candidates. Massive interactive binaries were, of course, proposed by people working on binaries. I myself and many others, including Franca, for example, have been advocating AGB stars because we had some familiarity with this kind of objects. Although, as I will mention in a moment, I have repented for this, and I kind of changed my mind. Finally, supermassive stars of order 10 to the 4th, 10 to the 5th solar masses have also been proposed as objects that would form in the nascent globular cluster and provide the material to make second generations. As I said, I opt for now, my best candidate goes to the massive interactive binaries for one reason. Let me say why I gave up with the AGB. And the reason is that if you want to have the AGB making the material, then you have to wait for order of 200, 300 million years. So how the things could be so unavoidable and yet require such an extremely long time interval between the first and the second generation, that makes me very, very skeptical that AGB stars are the prime contributors. And this, therefore, I tend to favor massive stars. But once, if we choose massive stars as the progenitors for the donors, so for saying, then immediately we have to know that 70% of all massive stars are in interactive binaries, and therefore, if massive stars are the producers, then binaries automatically win the stage. Now, the question is, if the massive stars are the donors, either single or binaries, they eventually undergo core collapse, eject metals, and 10 to the 51 Earths of kinetic energy. Or not, it's the question I will address in a moment. Now, 2G stars, most 2G stars, are not enriched in iron with respect to 1G. And so to make the second generation, we want the material lost by interactive massive binaries, but we don't want the supernova products. How to avoid the supernova problem? This is called, in fact, the supernova avoidance problems. To avoid the supernovae, it was proposed already 10 years ago by Krause et al. That above a certain mass, order of 20 solar masses, stars do not explode as a supernova, do not eject the envelope and 10 to the 51 ergs of kinetic energy, but silently sink into a black hole without ejecting metals and kinetic energy. Independent arguments for no supernova explosion in massive stars above a certain limit can be found in the references at the bottom of this view graph. And recently, I have been talking to supernova experts, and for them, it's no surprise that above a certain mass, stars may not make a supernova display. And the reason is that, in fact, at least from a theorists, always had a problem to get the explosions. And certainly the difficulty of making explosions for reasons we may discuss later increases with the stellar mass of these objects. So the solution that I adopt for the supernova avoidance problem is, in fact, that above a certain mass, we don't have supernovae. Thus, we don't have supernova feedback for 10 million years. So we are going to have a delayed supernova feedback. And what is the effect of a delayed supernova feedback? Now, this is the complicated story. The question is now, what sequence of events led to globular cluster formation with dimultiple stellar generation? We start inevitably with a giant molecular cloud inside a dwarf galaxy that becomes gravitationally unstable, collapses to high densities, and begins to form a massive cluster. If we don't have supernovae for 10 million years, and we don't have a feedback to regulate or stop star formation, then the giant molecular cloud would go into a runaway star formation process, which this kind of situation was called the overcooling almost more than 40 years ago by White and Rees, who figured out that in the early universe, in absence of any feedback, most baryons would have been rapidly turned into stars with extremely high efficiency. This was obviously not the case, because even now, only 10% of the baryons in the universe have been turned into stars. So something had to prevent this effect, this overcooling on a global scale. And this was, and to avoid overcooling, the supernova feedback was invoked, and still now is. What I am advocating, therefore, is that if supernovae are suppressed for the first 10 million years, because stars go into black holes, then you have absence of feedback for 10 million years, and the situation is similar indeed, is an overcooling case. Star formation peaks at the center of nascent globular clusters, but star formation had to also to go on in the host dwarf galaxy over a major fraction of the giant molecular clouds and part of the dwarf itself. A concrete possible example is shown here. The most violent formation of a massive and young cluster in the vicinity of the Milky Way is the well-known case of 30 Doradus in LMC, where you have a picture here. At the center, you have the cluster 2070, NGC 2070, and the center, and also you have the famous R136 nucleus. And the scale of this picture is 100 parsec. All these little spots, some white, some bluish, are young stars, massive stars whose age is in the color bar on the right side. So the situation I am suggesting is one in which the material that forms around the nascent cluster is polluted by the young stars that forms there and goes into a cooling flows converging towards the cluster and bringing second generation material to produce second generation stars. Material produced from first generation with the composition to make the second generation. Here you have, in fact, this picture shows what is the typical case of NGC 2070 in 30 Doradus, in which you have the star formation rate, the current star formation rate in this young cluster, and compare it to the star formation rate as a function of radius of various star forming regions in galaxies at high redshift and low redshift all over the place or within the galaxy itself in the lower path. So the horizontal black line marks the star formation rate required to make a 10 to the 6th solar mass globular cluster in 10 million years. And so you see that NGC 2070 in 30 Doradus is not far from that capability. Now, let me emphasize what are the advantages of such delayed supernova feedback. The first advantage is that it expands the mass range of donors. That is, it increases the availability of the available mass budget, because if there were not such a delayed feedback, that is, if all massive stars would explode as a supernovae, then from the burst of star formation to the first supernova, you have only 2 to 3 million years, and therefore, if supernova wipes out the gas after 2 or 3 million years, there will be no time enough for releasing the material required, all the material required to make the second generation. So that's the first advantage. The second advantage is that the absence of feedback favors continuum star formation, and therefore promotes the formation of second generation stars. And finally, it boosts the absence of feedback. Well, it's a consequence of the first two, in a sense. Boosts star formation efficiency that can go up to 100%, as we can say, as in the famous overcooling catastrophe that was envisaged would have happened in the early years. Now, suppose that this is the right way the globular clusters form. What matters in this in a broader context is the existence or not of this 10 million years delay in the feedback that results in overcooling, as I made. As I already pointed out, that in general, this will facilitate local burstiness in star formation. It will facilitate the formation of massive clumps in high redshift gas-rich galaxies, for example. It may help forming nuclear clusters in galaxies. It may facilitate the formation, as I said, of giant clumps of star formation. It may help to form extreme baryon concentration, because if you start forming a baryon concentration promotes star formation. If immediately you have feedback, this regulates and prevents further accretion of baryons into that particular spot. If you don't have the feedback, the accumulation of high density baryons is only favored. And finally, I wanted to mention this will facilitate the formation of massive galaxies at very high redshift, now found with JWST. And let me expand a little bit on this. Here we have a paper by Finkelstein of last year. You have the surface density of objects brighter than, as you can read from the caption, brighter than magnitude 28.5 at redshift larger than 8.5. And that's each object is one step in this plot in the upper panel. And in this magnitude is in the near infrared at 2.77 micron. In the lower panel of this figure, you have a series of lines of various colors, and those are essentially the theoretical simulations or semi-analytic models from various authors. If we focus, for example, on the green line, the light green line towards the bottom of the figure, which is the Millennium TNG, one most successful of the simulations around, you see that it falls short by roughly an order of magnitude compared to the JWST counts. The dot dashed line that is indicated by the red arrow is instead an upper limit, an upper limit to the possible formation of these objects from Berusi et al., in which they assume that the efficiency of converting gas into stars is at those redshift 100% inside dark matter halos that corresponding mass, which is to say is what you would expect in case of overcooling. So this indicates, it speaks by itself, and this is not so much emphasized in Finkelstein et al. Paper, but it could be interpreted that in these objects, that in fact most of the stars are younger than 10 million years, there was no feedback. It was really, they were in an overcooling phase. So that's if, in other words, if my suggested solution to the globular cluster issue is as I said, basically driven by the lack of supernovae for 10 million years after star formation, then this could help solving also this issue of the abundance of massive bright galaxies in the very early universe. I think this is basically what I wanted to tell you. I will thank you. And of course, I would expect a lot of controversy about this. So we may start to discuss about individual points as you like. Thank you.
Many thanks, Alvio, for this quite interesting talk. There are questions? Okay, I don't see the hand if someone...
Yeah, in case I see, I'll tell you. Anyways, okay. Alvio, if I may, well, actually, you said at the beginning that you have also an option for metal-rich globular clusters. So if you want to say something,
yes, and let me. I had a view on the metal-rich. The metal-rich globular clusters could not have formed into dwarf galaxies because dwarf galaxies are metal poor. So as simple as that. They are all found basically in the bulge. So they had to form in clumps inside the bulge or migrated there. But essentially, well, the paper it's quoted there is relative to an hypothesis that was made by Shapiro et al. A few years ago, in which the empirical evidence is about redshift 2 galaxies, in which that are rotating disks, very gas-rich, in which in these disks there are several very bright clumps of star formation, as revealed in particular but by H-alpha emission. And so they hypothesized that inside these clumps, globular clusters could form, and the clumps themselves will migrate to form the bulge. On the other hand, the bulge is about, in the galactic bulge, is about 20 times more massive than the stellar halo. The stellar halo is 10 to the 9 solar masses, and the bulge is 2 times 10 to the 10 solar masses. But it has about 10 times, well, yeah, perhaps 5 to 10 times less globular clusters than the halo. So the bulge, while forming a lot of stars, was substantially less able to form globular clusters than the star formation that led to the stellar halo. And this is a general problem, a general situation, I would say, with extragalactic, with other galaxies, in particular giant elliptical galaxies, where there is nearly half and half metal poor and metal rich globular clusters, but metal poor stars, there are very few. So the evidence was that the efficiency of globular cluster formation was much higher at low metallicity, which is to say inside dwarfs, than at high metallicity, and high metallicity is reached only in massive galaxies, when galaxies have reached already order of 10 to the 10 or more solar masses. So conditions conducive to globular cluster formation were much lower at the time of formation in the bulge than in pregalactic dwarfs. So this, what are the conditions to form a globular cluster? I would say that you need low vorticity, because if there is a lot of vorticity that is of angular momentum, it's a problem to get rid of it if you want to get a very compact situation. And also globular clusters are very round. In fact, if they rotate very slowly. So one may say first of all, in the bulge, it was much more difficult to form a globular cluster, possibly because very high gas densities coupled to low vorticity that were conducive to globular cluster formation were much rarer in the protobulge than in dwarfs. That's my 2 grain of salt about how the globular cluster might have formed in a metal-rich environment, and they exist. I mean, there are the 2 most metal-rich globular clusters in the bulge are about solar in metallicity.
Okay, thanks.
Yeah, question? Okay, in the meantime, maybe I can would like to ask you some point, Alvio. The first one is concerning the scenario for the formation of a metal globular cluster. Nowadays, we know that in many globular clusters, at least we are collecting evidence about this, Antonino and others are working on this. There is the clear evidence that the first generation has a spread in metallicity, okay?
Yes.
How this fit, what kind of constraint or problem this put on your scenario?
Yes, in fact, in some of the chromosome maps that I have shown, there are cases, about 10% of the clusters do show 2 things, actually. But most clusters actually do. The first generation is not a spot, but it's a line. I mean, it's elongated. There is a spread in something. And according to spectroscopy made by Anna Marino in particular, the result was that there is a small spread of iron, order of 0.1 dex, also in first generation stars. And this may indicate that the molecular cloud out of which the cluster started to form was not perfectly mixed in the first place. So you had there was the clusters, the material that formed the cluster was already enriched by some previous generation. Were not, even if a metal poor, let's say 100 solar or so, still there was a pedestal iron abundance to start with, and so that I would say is a possibility that the material was not perfectly mixed already. On the other hand, we are talking about time scales of order of a few million years, so it may be that, but that's a problem indeed. My guess is that it was not perfectly mixed. Then there is a second issue about the iron, is that there are clusters in which there is a parallel, in which the so-called chromosome map is split. There are not just one 2G sequence, but there are 2G sequences, and perhaps also 2 1G sequences. And this means that at some point, while the star formation was going on, a few supernovae started to explode before eventually the bulk of the supernovae came out and expelled the gas and did stop star formation. So the first few supernovae that exploded could pollute the material while star formation was still going on, but they were not sufficient to stop the star formation. So that I would say is a reasonable interpretation for this.
Okay. And the other curiosity is the following. You have mentioned the issue related to the formation of a metal-rich globular cluster, no? And you say that maybe the condition for the formation of this kind of cluster were different in the bulge with respect to the halo. But the point, my curiosity is, but indeed, it could be possible that in the bulge, a huge amount of cluster indeed formed in the past, and after they have been destroyed as a consequence of gravitational interaction. Because
Yes,
we are talking about two completely different environments.
I see the point. I see the point. On the other hand, there are something like I have a paper by Bika, Ortolani, and Barui,
yes.
in which they have they have all these. They have 40 clusters that apparently that are inside the 4 or 5 kpc from the bulge, but some of them are kind of metal poor, more metal poor than the metal than seen among the stars in the bulge itself, and so presumably they may actually be intruders from the halo. But there are order of at least 30 globular clusters that are presumably genuinely in the bulge. So, what was the question? Sorry.
The point is simply if indeed this would, the possibility that the globular cluster actually formed in big number in the bulge.
No. In fact, I started from this because I wanted to answer your question. So we have evidence that at least 30 globular clusters perfectly survive. And these are kind of dense, in fact, are those that presumably formed in the scenario that I have presented, that is in a runaway overcooling kind of sequence of events. On the other hand, certainly, like in the halo, the clusters might have formed which are less concentrated, less dense, and therefore more prone to have dissolved. Definitely. So, but to tell what was the original population and how many they were compared to the 30 survivors, that's difficult to tell, I would say.
So I would like to have a comment on that.
Mm.
So we know from the analysis of the specific frequency of globular clusters in galaxies, which is basically the relative number of stars in globular clusters compared to field stars. We know that the specific frequency is very high for low mass galaxies.
In dwarfs, indeed.
And it's very high for very massive galaxies. And then it's kind of flat for all, for the rest of it, for like the normal intermediate mass. So the scenario you said, I mean, it's kind of interesting, but then we need to know why then it is very efficient, the formation of globular clusters in massive galaxies. But besides this comment, if there are no other questions, I have a couple of curiosities, Alvio, unless you want to add something on that. So my curiosity is this. Pardon me if I'm wrong, but the point is that you basically destroyed what I studied as a student. So we don't have supernovae, the regular exploding type 2 supernovae for objects that are massive than 20 solar masses. You said that these are silent supernova. That's what you said, basically. Yeah. And then is that, so this is a specific property of the environment in this hypothesis? I mean, is it related to the fact that we are in a very high density region, where you have 10 to the 7 solar masses of star formation in a very narrow volume of space, and then what happened to the black holes? So these are primordial, they're very old ones. So do they cluster in this hypothesis toward the black hole center? So we should look for.
Let me try to answer. First of all, the idea that above a certain mass stars do not explode as supernovae is independent of the environment, I would say. The idea. Then we may discuss whether there are sufficient observational support for this ansatz. At the moment, there are some indications. Those that I had a few citation down below there. But for example, there has been the case of the so-called Adam star, which is a massive star in a nearby galaxy that has disappeared. One day it has disappeared. So this is one of the support cases. But definitely this is an ansatz, it is an hypothesis that has some attractive aspects, but I certainly must say it is not proven at all. It has some interesting consequences. And let me come to the point of what happens to the black holes. If well, there is no issue about that these stars, massive stars, eventually go into black hole. They all agree. The question is whether this is that going to the black hole is accompanied or not to an explosion. You see, so the problem of what happens to the black holes is independent of whether you have the explosion or not so strictly related, at least. Now, what happens is that certainly you can, if the IMF is Chabrier, for example, then you can easily calculate how many black holes you form. And the gravitational wave detections and of so many events by now are giving stricter and stricter limits to the mass above which and evolution ends up in a black hole. Now, the interesting aspect, so the black holes most rapidly, this is an issue, a problem in cluster dynamics, of which I'm not an expert, but we can talk about it. So the black holes are supposed quite rapidly to go into binaries if they were not binary from the beginning, because they are slower, more massive, and therefore they tend to kick out any companion when they encounter another binary. And eventually the battle is among binary black holes, because when two binary black holes interact, and the most probable outcome is that at least one black hole is kicked out at very high velocity and leave the cluster. So a good fraction of the original black holes that formed into globular clusters had been kicked out, not all, because most likely, you know that at some point it was kind of popular, the idea that emerging black holes seen in gravitational waves actually were coming from globular clusters, because globular clusters would be another nice place where a binary black hole gets tighter and tighter because of interaction with other stars, and so facilitate eventually the merging. So that I don't see a major concern about what happens to the black holes. I mean, and also I would repeat that the production of black holes above a certain initial mass, as opposed to making a neutron star that cannot be much bigger than a Chandrasekhar mass. That's something that is independent of whether you have or not a supernova display.
Thank you.
Thank you.
Any other question? the meantime that people think, I have another curiosity. Now your preferred candidate for as polluters are massive star in binary system. We know after more than 10 years of accurate spectroscopical measurement that the second generation star in the different globular cluster show very different chemical pattern concerning some clusters show evidence of correlation between S elements and light element and so on. If we take into account of this evidence as a rule, the possibility that indeed the candidate polluters are massive star have no problem, is able to just justify all the spectroscopical evidence, for instance, the correlation about lithium abundance and light element and so on.
I'm not sure it justifies, it explains all. In particular, you know that in some clusters, the part of least of the second generation stars show enhanced S process elements.
Yeah.
And this was taken for granted. It was HB. It was one pillar of the HB option. And I don't know. I have two possible ways to explore. The first is whether you know that also massive stars tend to produce S process, but only during core helium burning, and so it's not obvious that this material can come out and correspond to what we see. And the other possibility is that there is eventually a little bit of HB coming in, but in order to make the HB to contribute, one should wait at least 30 million years. And this makes a time much longer than, so the question of age of the S process is intriguing. In fact, it's not explained in my scenario. Naturally, it's not.
But I don't remember now. But there is an indication that the presence of S element spread is correlated with the presence of a metallicity spread in the cluster. If we exclude the case of Omega Centauri,
yes. Now, I don't think we have enough statistics because the S process have been seen in only a few clusters. In fact, only a few.
They show a metallicity spread, all of them, because if they show,
I will have to check. There's certainly a point. I have to talk with Anna, because Anna knows about these things much better than anybody else.
Sure.
Yeah, the other thing, because some of you actually are experts in stellar evolution, is the question, but how good, and this is something I'm not sure myself, how good are the massive interactive binaries for making the right stuff? And for this, well, the interactive binaries have one attractive aspect, which is the fact that most of the envelopes are ejected at a low speed during common envelope events. And so this is all energy that does not, there is no feedback, in other words, as opposed to stellar winds, because these are stellar winds may also be a problem, perhaps not in metal poor stars, because the winds are not so fast, but in metal rich to avoid the feedback from winds, not from supernovae. That is easier at low metallicity. But the question is, in order to have the right chemistry, these massive stars should experience extra mixing, deep circulation, meridional circulation, such that the envelope down to the temperature of order of 70 million degrees is mixed. And I don't know, honestly, nobody knows for sure whether this is happening or not. Only observation actually would tell. And how rapidly is this material taken up? This is a whole line of research on its own. by the way, that would be important to pursue. The fact that the binary, the fact that stars are binaries, this enclosed one, would promote co-rotation and therefore enhance meridional circulation, perhaps. And the best thing would be to look spectroscopically to these massive interactive binaries that have been looked for, in particular by Sana et al. In this classical paper, that figured out that 70% are in fact interactive binaries, and see what's the CNO on top of it. What's about oxygen and sodium?
Sure.
That would be the real. But these objects sometimes are very young, and so they may not have time enough to bring enough material to the surface. So statistics would be required. It's a big project to start, in fact. And I have not explored all the literature, but I'm sure that there is something on that as well.
Maybe Enzo want to say something.
Thanks for the talk, but I've been interrupted 4 times along during the talk. Anyway, so maybe I missed something.
And do it now.
I will do the registration of the talk because it was interesting. But I have just one curiosity. On your scenario, do you think that this can modify our expectation on the supernova rates in galaxies? Because, of course, there are an error bar which is large, so
yes,
it's difficult.
Yes.
But maybe on times, this may be
Well,
another situation.
The majority of stars that die with core collapse are between 9 and 20 solar masses anyway.
Mm-hmm.
So if you lose the most massive ones, you don't decrease the supernova rate by much. Instead, I'm more concerned about the metal yields.
Yeah.
Because then you would lose all the nucleosynthesis otherwise in the classical papers of nucleosynthesis, that in fact the assumption there is that all stars up to 100 solar masses do produce a supernova. Yes. And produce a certain amount of oxygen, silicon, magnesium, and so on and so forth. Mm-hmm. So the concern, the collateral damage of my hypothesis is in fact the most serious one, is on the front of the yields rather than on the rates.
Okay. Thank you.
If there are no other questions, we can thank again Alvio. Do you see something, Michele?
Nothing to say. Thank you.
Okay. So thank you to everybody. Ciao Alvio. Thanks a lot. Many thanks.
Ciao Alvio, grazie.
Ciao Alvio.
Grazie.
Ciao a tutti.
Grazie.
Thank you.
Interrompi la registrazione.